When you adapt a large language model to a new domain with few shot examples, which examples you pick matters enormously. Pick the wrong ones and the model inherits their biases. Pick the right ones and performance jumps. Prior methods select examples using output-level signals. They look at how uncertain the model is about each candidate, or how semantically similar the candidates are to each other using external embeddings like BERT. Both approaches are proxies. Entropy is unreliable because language models hallucinate confidently. External embeddings assume semantic similarity means knowledge equivalence, which is false. A new method called NeuFS replaces both proxies with a single principled signal, the model's own internal neuron activations. It wins all 4 MMLU-Pro reasoning benchmark cells across 4 different models. NeuFS works in 3 stages. First, it extracts which neurons fire for each candidate example. For every feed-forward layer, it computes the contribution of each neuron to the predicted token using early unembedding, a technique that projects neuron outputs back into vocabulary space. Neurons that contribute strongly are kept. The result is a sparse set of activated neurons for each sample. Second, it diversifies the demonstration set by clustering these activated neuron sets. It uses Jaccard distance, measuring how much 2 samples share activated neurons, and runs K-Medoids clustering to pick diverse representatives. Third, it scores each candidate by neuron consensus. Fewer shared activations means lower consensus, which prior work links to higher hallucination risk. Samples with low consensus are the most informative to label. The 2 signals combine into a single score for each cluster. Diversification is measured by Jaccard distance to the cluster Medoid. Informativeness is measured by the count of unique neuron activations. The final score blends them with a weight tau. Tau near 0 means prioritize diversity. Tau near 1 means prioritize low consensus samples. The method selects the highest scoring candidate from each cluster, producing a demonstration set that covers broad knowledge and focuses annotation effort on the most uncertain examples. The key insight is that both signals come from inside the model, not from output proxies or external embeddings. On the MMLU-Pro reasoning benchmark, NeuFS wins all 4 aggregated accuracy cells. On Llama 3.18 billion, it reaches 0.327, beating Patron at 0.313. On Qwen 3.8 billion, it reaches 0.418, beating Patron at 0.416. On the smaller models, Llama 3.23 billion reaches 0.251, and Qwen 3.4 billion reaches 0.452. The largest margin is on Qwen 3.4 billion, where NeuFS leads by 2.2 percentage points over entropy-based selection. Internal neuron dynamics beat combining semantic embeddings with predictive uncertainty. Ablation confirms that sparse neuron activations are a better sample representation than dense embeddings. Replacing neuron sets with Qwen 0.6 billion decoder embeddings drops average accuracy. Replacing them with SimCSE BERT embeddings drops it further. Neuron activations beat both on all 3 dataset averages. This validates the core claim. The model's internal sparse activation patterns capture something about sample relevance that dense semantic vectors miss. The statistical evidence is strong. A 2-sample t-test shows that incorrectly predicted samples activate significantly more neurons, with t equals -3.57 and p less than 0.001. Lower consensus correlates with higher error rates. And a sliding window experiment shows that using lower consensus examples as demonstrations measurably improves inference accuracy, with Pearson R equals 0.67, again p less than 0.001. The neuron consensus signal is not just theoretically motivated, it predicts which examples are most valuable to annotate, but NeuFS is not uniformly dominant. On the classification tasks, EDU feedback and TREC, it is competitive, first or second ranking, but not the clear winner. Entropy diverse and fastboat K beat it on several cells. And there is a hyperparameter honesty problem. The deployed values for the activation threshold and the scoring weight fall outside the paper's own ablation sweep range on some configurations. The paper shows a sharp performance drop at tau equals 1 on some models, yet deploys tau equals 1 for others. Now, the scope. First, NeuFS requires open model weights. You need access to the feed-forward layer activations and the unembedding matrix. This will not work with closed API models like GPT-4. Second, it has higher compute overhead than retrieving static pre-computed embeddings, because it must scan every candidate through the model. Third, no model larger than 8 billion was tested, so scaling behavior is unknown. Fourth, the evaluation covers only 3 datasets. Code is available on GitHub. NeuFS shifts the few-shot selection paradigm from output-level proxies to internal neuron dynamics. Sparse activated neuron sets beat dense embeddings for representing samples. Neuron consensus predicts which candidates are most informative to annotate. The clean contribution is the paradigm shift, not uniform dominance on every benchmark. Subscribe for the next paper breakdown.